so we were studying dual slope voltmeter, and before proceeding on further discussion on this topic, I thought I would just tell you a small story, and the story is like this. So, suppose there is a building, a multi-storied building. Okay. So, this is a multi-storied building with many floors, and there is an elevator, a lift. Okay. So, actually there are two lifts. This is one and this is another, both hanging from a pulley. Okay. So, this is a pulley which can turn, and these two are hanging from each other. Okay. And actually the scheme is so that, or the length of this wire or string is so long that if one elevator is at the ground floor here, then the other elevator is at the top floor. Okay. And these two are of equal weight. Okay. And you can think that the entire arrangement is somehow sealed into a tight container. Okay. So, something is filled in it. It could be air, it could be some viscous liquid, water, oil, anything. Okay. So, what happens if these two are of equal weight, then they will just stay as it is, they will not move at all. But if I put any extra weight, suppose a person enters this elevator, then this elevator becomes heavier, and then this will fall down, this will go up. Okay. So, this is how it works. So, people can only come down through these elevators, no one can go up. It is useless, but let us see it. Okay. So, somebody can enter this elevator, then this elevator will come down, this elevator will go up. Okay. And so, it is like this. So, this will go up, this one will come down, okay. And then another person can enter this one, this man can leave. So, then this one will come down, this one will go up. Now, the two elevators, when they are vacant, they are empty, they are of equal weight. So, the weight difference is the same as the weight of this person. Okay. Say call the weight of this man is W. Okay. And now, how fast this elevator will fall, that will depend on the weight of the person entering or leaving the elevator. Okay. So, if a person with weight W enters here, so this man has a weight of W, then the speed at which this will fall is proportional to W. Okay. Call it kW. K is a constant. Okay. And K depends. So, let me write first that speed of falling, speed of coming down is equal to K times the weight. K is a constant, and it may depend on the, say, the fluid with which this chamber is filled, air or water or oil, whatever. Okay. So, depends on the fluid, depends on the viscosity of fluid and other factors. Okay. Now, this elevator is in a sense useless, because people can only come down from top, no one can go up. But this elevator is useful because one can use it to measure the weight of a person. Okay. So, we may use this elevator to measure the weight of a person. How? It is simple. So, say this height is h, okay. Then one may measure the time required for this elevator with the person to come down through this height of h. Okay. If t is the time required for a person to come down, then that okay, h by t, this is the speed, and this must be equal to, according to this, k times weight. So, this is the weight. Now, h is known. So, this h is known. We know the height of the building. This time required for the person to come down can be measured, and k should also be known. So, this constant should be known. So, then you can measure w. Okay. So, this is basically we can measure the weight or how heavy a person is by measuring the time required for him to come down. If the person is heavier, he will need smaller time, and vice versa. Okay. So, this is the idea. So, with which we can measure the weight by measuring time, right. Now, there is a problem. The problem is the weight which we measure as this factor h by t by k. Okay. The problem is if we do not know k precisely, or if our clock or stopwatch is running faster or slower, then w will be wrong, estimated w will be wrong. Right. So, this is the problem, because if say the clock is running faster, then we will measure the time required to be smaller, and then w will be of course wrong. If say this is filled with some fluid whose viscosity say depends on like air temperature, etc., and if say this viscosity is changing, the factor k will change. So, therefore, this will also change and will encounter an error. Now, we propose a modified scheme, okay, a solution where this w will be, or w measured will be independent of t, that means our clock, whether that is fast or slow does not matter. So, it will be independent of the clock and k, that means our knowledge of k. Okay. We will somehow make the measured value of w independent of these two factors. How? So, the scheme is as this. So, we will first put a man whose weight is precisely known, say it is precisely 100 kg, maybe too heavy he is, but okay, he or she is. But so we will put first a man with weight 100 kg in the elevator and measure required time to come down. Say that man with weight 100 kg comes down in t0 time, right? Okay. Then so this is step 1, and in step 2 what we will do, we will put a man with unknown weight, okay, call it Wx, and you can call this weight of the previous man as W0. Okay. So now we will put the man with unknown weight Wx and measure the time for him to come down. Now what we will do, you can guess, we will basically compare these two times. How fast the previous man, the standard man, reference man, whose weight is precisely known, it is 100 kg. So how long he took to come down versus how long this unknown man took to come down. So we will compare these two time, okay, and from this we will estimate the unknown weight, okay, and then it will be independent of whether our clock is running faster or slower, or whether we know the this constant k precisely or not. It will be immaterial. How? Let us see. So we can write, see, you see, from this previous rule, okay, height by, call it t0, this is the speed for the man, reference man to come down, this is equal to kw0, which is 100 kg, we know. And similarly we know h by t1, or call it tx. Tx is the time for the unknown man to come down, okay. So call this equal to tx. So this is the speed for the unknown man, and this should also be equal to kwx. Now we will divide this equation one with the other. So you see, we will get this. So let us divide this by this. So we will have, so h and h will cancel. So let me write here, h and h will cancel, we will have tx by t0. So we are dividing this by this, tx will go up, and this will be equal to w0 by wx. From this you can write wx, unknown weight, is equal to w0 t0 by tx, okay. And you see the factor k is gone, factor k is gone, k is not present. So we do not need to know the value of k at all. And secondly, you see that we have a ratio of 2 times, okay. So now if we measure both this time with the same clock, then whether the clock is actually running faster or slower doesn't matter, because we are measuring with the same clock. So if this is faster, this is also faster, their ratio will remain same, okay. So also let me write that we should use same clock to measure both t0 and tx, okay. So these are the two observations. So this is how we can make the measurement of weight independent of this whether our clock is correct, whether we know the factor k correctly or not, okay. So this was a thought experiment, fictitious. I do not really know whether it really works like this or not, but this is only to understand our scheme of voltage measurement with dual slope voltmeter, digital voltmeter. Okay. So, what do we have in a dual slope voltmeter? Now, let us look at, go back and look at. Okay. So, this was kind of a schematic of a dual slope voltmeter. This is yet incomplete schematic. Okay. This is incomplete schematic. We will complete it soon. Okay. So, let me take it from here to here. Okay. So, just you see what we do. So, we have two voltages. One is known VR, this is precisely known. VR, this one is precisely known, or we assume that this is precisely known. If it is not precisely known, then we will have some error. Okay. This is the assumption. This is precisely known, this is unknown. Now, what we do? We first connect it to, say, this switch, this integrator, we connect it here to the unknown, and then let this voltage increase for a fixed amount of time. Okay. Now, so this voltage will increase by some amount which depends on Vx. Higher the Vx is, the slope will be higher, so it will go further. If Vx is lower, the final value will be smaller. This is a fixed time interval for which the integration is carried out, right. And then we switch this switch or integrator to the reference voltage, and then we measure how long will this integrator take to discharge. This is negative, this is positive, that was the assumption. So, when we connect it here, the voltage increases, and when we connect it here, the voltage decreases. So, after this, this voltage will come down, okay, and this will come down with a fixed slope, because this is a constant voltage, known voltage. So, this slope is constant. Now, how long it takes to come down, that will tell me how large this Vx was. Because if Vx was larger, then for the same amount of time, this voltage will go further up, okay, and then when it comes down with the fixed slope, so it will take longer time. So, if Vx is larger, it will take longer time to discharge. That is how we measure this unknown voltage, and in this way we make the measurement independent of this constant C, which is somehow gets multiplied with this input voltage, whatever it is, here or here, and that defines the rate or the slope. Now, you know, if C is the same C is applied for both integration and deintegration time. So, the effect of C gets cancelled, just like the effect of this factor k in this experiment. Okay. Similarly, the effect of C will not matter. Similarly, this counter is now driven by some clock generator. Now, if the clock generator starts to run faster or slower, what will happen is that this time and this time they will be shortened or elongated by equal proportion. So, therefore, it will not affect the measurement, and that we have seen in our previous day with thorough derivation. Okay. So, we have seen how the frequency of the clock does not matter, it gets cancelled. But the best way to understand it, I think, maybe if you think about this hypothetical experiment, okay, it will help you to understand the principle of this dual slope integrator. It's dual slope voltmeter. Okay. Now the next thing that we will do is this. We will draw a better schematic. This is a schematic, and I already told you that this is incomplete schematic. The next thing we will learn how to draw a better schematic. Better means, of course, that won't be the best, but that will be better than this, because that will have more information, more detail than this schematic has. This is fine for understanding some basic things, but to make it more complete, we will put more detail in this. And at the same time, we will keep our thoughts going on. So let me write more detailed schematic of a dual slope voltmeter. Okay. So just listen it carefully. Okay. Otherwise, you may get lost. Firstly, what we will do, we will take a clock generator or a crystal oscillator, for example, say it generates signal, generates square wave with a frequency, say 1 megahertz. Okay. So let me just take also an example. So this will also help you in solving numerical problem if you follow this carefully. So say this is 1 megahertz. So this is frequency. So if this is the frequency, what can we write about time period? Time period will be 1 microsecond, right? 1 microsecond. Now we can take a frequency divider. What is the function of the frequency divider? The function of frequency divider is as follows. So it takes a high frequency input and it gives out a low frequency output. Okay, so this is high frequency input and this is the output, which is of much lower frequency. Say I take that this is divide by 1000. So then this is 1 megahertz. Here I write 1 megahertz. Then this will become 1 kilohertz, right? If it is divided by 1000. Okay, I'm just taking arbitrary numbers just for as an example. So this is 1 kilohertz signal. Now if this is 1 kilohertz signal, which means say from here to here, this is one time period. How much will be this? This will be 1 kilohertz. So this will be 1 millisecond. Okay. Let me do this. Let me make it divide by 2000. Then this will be half 0.5 kilohertz, and then this will be 2 millisecond. Okay. I do it on purpose so that calculation becomes easy. So this is 2 millisecond, and then this half of it. So this is the on time. Okay, from here to here. this will be 1 millisecond. So this is 1 millisecond, and here another 1 millisecond. Okay. So 1 millisecond on time, 1 millisecond off time. Now what we will do, we will feed this signal, say to a, call it a control unit, which will control this switch position. Okay. So by this dotted arrow, I mean that this control unit will control the switch position. How? Let me write that. So this switch, okay, which is K, switch K will be with Vx, will be connected to Vx, that is unknown voltage, when say this is high, this signal, when this signal is high. Call this what can I call this signal as A. When A is high and connected to Vx, Vr, that means here when A is low. Okay. So that means, so this input comes here and this control unit will accordingly change this switch. It will, for say first 1 millisecond, so first 1 millisecond it will connect it here to Vx, and next 1 millisecond here, when this is low, it will connect to this minus Vr. Okay. So for first 1 millisecond it will be here, and for next 1 millisecond it will be connected to Vr. This is the task of this control unit. Okay. Now, okay, so if so, then what will happen? Then in first 1 millisecond, let this be time, call this is Vy, right? So first 1 millisecond, this is 1 millisecond, this is 2 millisecond. So starting from here, this will go up, this is Vy, okay, this voltage, it will go up, and it will depend on how much it will go up, that will depend on the value of Vx. Okay. So it can go up like this or this, depending on the value of Vx. Then next 1 millisecond here, it is connected to Vr, and Vr is negative. So now Vy will discharge. So if it is here, it will come down like this. If it is here, then it will come down like this. And if it was here after 1 millisecond, then it will come down like this. Okay. And we will basically measure how long it takes to come down. So if this is the time, okay, call this, what can I call? Tau. Okay. So tau is the discharge time or deintegration time. So if tau is larger, that means Vx is larger. If tau is smaller, then Vx is smaller, right? Okay. And let me for you just do the derivation, the maths once again, which we did in the previous day. Okay. So how much is this value or called, sorry, this okay, let me make this let me make just one of them solid and other as dotted. So this solid one is a particular case, that is a particular value of Vx. Okay. So what is this value? This height. Okay. This height is call this what can I call it VH, this height, VH, this voltage. So VH is how much? This is nothing but, so the voltage increases with a rate of C multiplied by Vx, C Vx multiplied by T. What is T? T is this time. Integration time. T is integration time or charging time. Integration time. Okay. So T is integration time, tau is deintegration time, discharge time. This is charging time, this is discharge time. Okay. So this is Vh, right? And from this side I can also write that this Vh is also same as reference voltage Vr multiplied by C multiplied by tau, right? This is the rate of fall here, rate of fall multiplied by this time is the total fall. This is the rate of rise multiplied by time is the total rise. And this rise, this fall are equal, so I equate this. And from this I can write Vx is how much? Vx is, so C cancels, Vx is Vr tau by T. Vr tau by T. Okay, so that was the rule. Okay, so now the next thing is that how do we measure this tau? Okay, we will basically measure this tau by measuring the number of cycles of this signal. Okay, so what we can do, let me erase this. Let me connect it to here. Okay, so then what happens? This crystal oscillator is, or this clock generator is also driving this counter, and then by watching the value of this counter I can measure time elapsed, right? Now one important thing is that this counter must start okay, what do I want to measure? I want to measure this time, this deintegration time, right? So I must keep this counter on only during this time from here to here. Okay, so I actually have this comparator. What is the task of this comparator? When the value of Vy goes below 0, then this will become, output will become low. So this is low when Vy less than 0. So that means after this point, that means in this region here the counter will not continue to count. Okay, so this is the task of this comparator. So the comparator stops counting after this deintegration is complete, after Vy has reached the value of 0. Okay, and what I will do, I also have to make sure that the counter is not counting in this region, right? Because I only want to measure the time in this region. Here, see my pointer. I do not want to measure the time here. So for that, what I will do, I can take I mean, this is some very easy. What you can do, you just can take this signal, and if this is 1, if this is 1 means what? In this region, the control unit will connect the switch to Vx. Okay, that means this is the integration time. So that means this part is the integration time. Okay, this is the position. This is the time when the integrator input is connected to Vx. So here I do not want the counter to count the time. So what I can do, I can connect a NOT gate and then connect it here. So that means the counter will count only if this is, only if here it should be high, that means here it should be low, then only the counter will count. So here it low means here. So that means only in this region. Okay, so from 1 millisecond to 2 millisecond, in this region this will be on. Okay, so let me draw it bigger. The same diagram I will draw bigger, as big I can draw here. So this is 1 millisecond, this is 2 millisecond. Okay, this 1 millisecond Vy increases, and here connected to Vx, unknown source, and here we have connected to Vr, right, this reference voltage. This is the deintegration time. Okay, now in this region, this value, call this signal, what can I call this B. In this part, B is low. Okay, so counter doesn't count, no counting, because B is low in this part. Okay, and also in this is basic. Let me also draw this signal on the same axis. So this is the signal I have named A. So this is this A. Let me draw this here. Okay, so this is high and low here up to 2 millisecond, and then it's high again. So this is signal A, right? So this is signal A, which is here, and in this region I am repeating again and again so that it is clear to you. I know I am repeating many a times. Okay, so in this region switch is connected to unknown voltage, in this region switch is connected to Vx. Now out of the this part here, okay, in this part will the counting happen? No. So here also no counting. Since Vy is low. So this is in this part. Okay. So in this part, in this time, output from the comparator is low, so no counting happens. Here, due to this input, the counter will not work. Only in this part the counter works. Okay, so here, so the counter value tells me this time, right? The counter value will tell me only this time. Note it very carefully. And now one more functionality you may require is that, so at this moment, okay, when the counter starts, so at this moment, so this is the instant, so this is counter starts, so at this moment we may need to reset the counter. Okay. So how can you do that? So you can, so there are many possibilities. You can just possibly take a reset input, and you see, so this is a moment where we have a falling edge of this signal A. So we can take a negative edge triggered reset based counter, and then you can connect this. So this will ensure that at this falling edge, when the counter starts, the counter is reset. Okay. So this is a better schematic, in a sense it contains more detail. Okay. So I request you that you read this also from the book, try to understand. If you do not follow, you can ask in the forum, we will try to help, and solve some problems that we will give in the tutorial, because we often find students are confused in this topic, although it's very simple if once you understand it. Okay. So that's the main thing about the dual slope voltmeters, digital voltmeters. Thank you.